So far, we have seen physics puzzles where the acceleration is constant. Those puzzles can be solved using the toolbox equations. In this video, we will see how to solve puzzles where acceleration is not constant. To solve these cases, we need to use calculus. Look at this example. The position of an object with respect to time is given by the following equation. Position is equal to 0.5 t squared minus t minus 1. Solve for velocity and acceleration as functions of time. Here, time is given in seconds and position is measured in meters relative to the origin. We know position as a function of time. We need to find velocity by taking the first derivative and acceleration by taking the second derivative. In this question, we were told that the position of the object was being given by this equation, 0.5 times t squared minus t minus 1. So how do we determine the velocity? It's easy enough. Since we've been given the position as a function of time, the velocity of the particle is simply going to be the derivative of the position. Because that's the definition of instantaneous velocity. Now, let's work out that derivative on a term-by-term basis. Here we have a polynomial term, 2 times 0.5, that's going to give us 1, and then we drop the exponent by 1, that's going to give us t. Here we have negative 1t, and when we take the derivative of that, the t goes away and we're left with just negative 1. So this then is the velocity of the particle, t minus 1. What if we wanted to find the instantaneous acceleration? Start with the acceleration, and remember that acceleration is equal to the derivative of velocity, which is equivalently the second derivative of position. The derivative of t minus 1 is going to be, this is a t term, that is t raised to the first power, so we just need to take its exponent. That's 1. And the negative 1 will drop away. So the acceleration of this particle is 1 meter per second squared. And if we wanted to be really rigorous about it, we would say 1 I hat meters per second squared. So what does it look like when a particle moves like that along the x-axis? Well, there's a way to show what it would look like using your calculator. Here's how you would do it. I'm going to set my calculator into something called parametric mode. That means that it will select, or it will display x with respect to time, rather than having an xy graph. I will also set it to dot mode rather than connected mode. A parametric function is one where both x and y are functions of time. So for x, I will punch in the position function that we used. So that's 0.5 t squared minus t minus 1. And for y, I'm just going to put in some dummy function so that we can clearly see when the particle reverses course. I'm going to set my window as follows. Minimum time as being 0, maximum time as being 10 seconds, and we'll see where the particle is every 0.1 seconds. I'll set x to range from negative 10 to 10, the scale of 1, and y to scale from 0 to 2 with a scale of 2. Now, let's take a look at the graph that results. We will see what the motion of the particle is along the x-axis over time. we see the particle start from x equals -1. It reverses course for a fraction of a second, and then it stops, and then it starts moving in the other direction, gaining speed as it does so. So this is a visualization of the motion of the particle. Here's another example. The acceleration of an object over time is given by the following equation. Acceleration is equal to 6t minus 12. Solve for the velocity and position as functions of time subject to the following conditions. The velocity at t equals 0 is 11, and the position at t equals 1 is 0. Now we know the acceleration as a function of time. We'll solve this puzzle by integrating the acceleration to find the velocity, and integrating a second time to find the position. As you'll see, you need to be given initial value data for the variables for each integration you perform. 2 integrations means 2 initial values. So here's the information we were given. The acceleration as a function of time is given by 6t minus 12. And implicitly, there would be an I hat meters per second squared afterwards. So let's work out what the velocity must be. The velocity is the antiderivative, the integral of acceleration. So what we have to do is to go through these two terms and take the antiderivative step by step. So, what function, if I take its derivative, gives me 6t? Well, if this is t to the first power here, then there must have been a t to the second power here. And a 2 multiplied by what gives me 6? 3. Minus. A constant term in the original becomes a constant multiplied by that variable. And finally, we have to add the ubiquitous plus c to account for whatever the initial value of the integral was. Now we need to figure out what the value of c is before we can proceed. Now we were told that the initial value of velocity was equal to 11. 11 I hat meters per second. C is whatever the value of velocity is whenever t is equal to 0. So in this case, that would just be 11. So we would end up with v is equal to 3t squared minus 12t plus 11. And this then is the expression for the velocity with respect to time. Now, to work out the position with respect to time, we just do this entire process all over again. This time we need to integrate the velocity. So, what do? We find the antiderivative of these term-wise. The antiderivative of 3t squared, well, t squared is going to become t cubed. And when you increase the coefficient by 1, then you have to divide the original coefficient by the new exponent. So that's going to give us 1. So the integral, the antiderivative of 3t squared is t cubed. Minus. This t over here becomes a t squared. And we divide negative 12 by 2 to give us negative 6. Plus. The plus 11 is going to become an 11t. And finally, we add the plus c. The position at a time of 1 second is equal to 0. So what we'll have to do is we take the value of 1, we plug that in for t, and we work out what c is equal to. So what all of this means is that 0 is equal to 1 cubed minus 6 times 1 squared plus 11 times 1 plus c. Work all of this out and you get 1 cubed, 1 minus 6 plus 11 plus c. So since 0 is equal to 1 minus 6 plus 11 plus c, 1 minus 6, that gives us -5, plus 11 gives us +6, so c is equal to -6. So that gives us an overall equation of x is equal to t cubed minus 6t squared plus 11t minus 6. Now, let's see what the graph of this latest function would look like. I'm going to enter in the function for position in the parametric equation. So that would be time cubed minus 6 times time squared plus 11 times time minus 6. And the mode that I'm going to use is parametric, but also dot mode. I'm going to use the same window as before, but I'm going to only examine it from 0 to 5 seconds with a time step of 0.05 seconds. So I will see what its position is every 1/20th of a second, every 0.05 seconds. Now let's graph it. What we see here is the particle begins at x equals -6. Initially it's moving quite quickly, but then it slows down until it reaches a stop at roughly x equals 1. It reverses position and reverses course until about x equals -1, and then it reverses course again and starts speeding up. Here's yet another example where acceleration is known and velocity and position must be determined. The acceleration of an object over time is given by the following equation. Acceleration equals 2 times the quantity 3t plus 1, all raised to the -2 power. Solve for velocity and position as functions of time subject to the following initial values. The velocity at t equals 0 is -2/3, and the position at t equals 0 is 0. Here is the acceleration function that we were given. A is equal to 2 times the quantity 3t plus 1, all raised to the -2 power. We want to figure out what the velocity is and what the position is, both as a function of time. So, let's start with velocity. Velocity is equal to the integral of acceleration with respect to time, which would be equal to the integral of all of this mess with respect to time. Now, the 2 is a constant over here, so it comes out of the integral. And so we're left with that. Now, we just need to integrate this quantity over here. How do we do that? Well, this is basically a chain rule being done backwards. You'll remember that when we were talking about derivatives and you have a chain rule, you have to take the derivative of the outside and the derivative of the inside. So over here, you have the derivative of the outside. So what outside would have this as its derivative? The answer is 3t plus 1 raised to the -1 power and then multiplied by -1. So if you were to take the derivative of this, this -1 would come over here to give you a +1 outside the parenthesis, and the -1 would be dropped to a -2. But you then need to take this quantity and you need to multiply it by 1 over the derivative of the inside. So this is going to account for the fact that when you take the derivative of this, the derivative of the inside gets multiplied. So now the derivative of the inside has to get divided. So that means that we need to divide by 3, or equivalently, multiply by 1/3. And this whole thing has to have a c added to it. So this entire integral works out to negative 2/3 of 3t plus 1 raised to the negative 1 power plus c. We were told that when t is equal to 0, that velocity is equal to negative 2/3. If that's the case, and we plug in 0 over here, then that means that negative 2/3 multiplied by 3 times 0 is 0, plus 1 is 1, raised to the negative 1 power, plus c, would all be equal to negative 2/3. 1 raised to the negative 1 power is just 1. Negative 2/3 times that would be negative 2/3. So that works out that c is equal to 0. So now we have an expression for the velocity. The velocity is equal to negative 2/3, 3t plus 1, all raised to the negative 1 power. And c is equal to 0. Now, let's work out what the position is. We need to take the integral of the velocity. Again, the constant term out front can be taken outside the integral. And we're left with the integral of 3t plus 1 taken to the negative 1 power dt. So, again, this is a case of undoing a chain rule. And the rule here, in a nutshell, is take the antiderivative of the outside, that would be ln of 3t plus 1, multiply it by 1 over the derivative of the inside, that's 1/3, and then add c. So, simplifying all of this, we get negative 2/9 times ln of 3t plus 1 plus c. So when the time is equal to 0, we were told that the position was also equal to 0. So now that we've solved this antiderivative, we just needed to figure out what c was. So x plus 0 is equal to 2/9 times the natural logarithm of 3t plus 1. Now, 3 times 0 is 0, plus 1 gives us 1. The natural logarithm of 1, that's the ln of 1, is 0. So this entire term over here works out to 0, which means that we get 0 equals 0 plus c, so c equals 0. And the position is equal to negative 2/9 the ln of 3t plus 1. Now, let's take a look at what this most recent example looks like, the position of this most recent particle. I will go into parametric mode, and once again, I will insist upon dot notation. This time I'll set the y value to just be equal to 1. That's the dummy value. And I will write out our function, negative 2 divided by 9 multiplied by the natural logarithm, ln, of 3t plus 1. Now this time I'm going to use a t minimum of 0, a t max of 200, and a t step of 1. So we'll see how this moves over a period of 200 seconds. I'm also going to set x min as -2 and x max as 2. So what we see is the particle initially starts at a fairly high speed, but it gradually slows down, never quite stopping, but definitely slowing down as it keeps moving. This video has gone over the techniques of solving puzzles where acceleration is not constant. These types of questions crop up in fields like aerodynamics and hydrodynamics, so it's important to know how to solve them.